Okay, so here we have a question about electric fields, forces, has a little bit about electric potential, and brings some Newton's laws stuff back into it. And so the first part is purely a sketch, right? We have to draw what the electric field looks like due to the 2 point charges. And so I'll put my two charges in. And this one, right, it's qualitative. You don't need to be mathematically precise, but there's some things that you definitely have to do. These charges we're told are both positive. That means the field lines need to point away, right? No matter what I do, the field lines all have to point away. And second of all, since both charges are positive, sort of all the field lines have to sort of repel from both of them, right? There's no field line that goes from one to the other, which kind of is what I meant when I said they both have to point away. And then to draw the field lines in, you kind of just have to think about what you know about the motion of objects. So for example, if I were to put a proton right there, I have to ask myself, how would it move? Well, it's going to be repelled from both of those, but it's going to be repelled from the close charge, and it's also going to be repelled by the other charge, but less so. So it's going to kind of go up that way, right? Up and away. And if I put one down here, it's going to do pretty much the same thing, right? But mirrored. So it's going to do like that and that, so it's going to go kind of like that way. And if I put one like right here, now it's repelled this way and only a little bit more weakly that way. So it's also going to be going down, but maybe a little bit more away, kind of like that, right? And so these kind of things give me an idea of how stuff is going to move, right? Because the fields are going to tell me about the force is going to tell me about the acceleration. All right, so let me get rid of all of that. And the other thing to keep in mind is that we know what the field of a point charge looks like. And so when we're only near one of the point charges, it should pretty much just look like the field of a point charge. So right, so like this should just point away, this should just point away. And here, right here, as we get closer, right, we know this should point radially away, roughly, radially away. But it also should sort of bend more away, because the other charge repels as well. So right, it's like something that's getting right here is getting pushed both down by the first charge and then also away by the second. And then for a field line that comes out kind of like this, right, it's going to have to curve around kind of that way. Right? And this one's going to curve around kind of that way, something like that. And so that kind of qualitatively gets it right. Right? That's the idea for that one. All right, so that's A. It should look something like that. You should make sure to use the whole space, right? If I just drew field lines here and here, I wouldn't really fully answer the question. I have to include that central area too, at least the best I can. All right, so part B, electric potential at point A, which is midway between the charged objects. So the electric potential of a point charge is KQ over R. We care about the electric potential at this point right there, right in the middle. There are 2 point charges that affect that, so the electric potential is V1 plus V2, right? The electric potential of both charges. Notice there are no vectors here, right? These are just numbers. So all I need to do is write down, right there, KQ for both of them, right? Because K is a constant, they're the same charge Q. And now we need to figure out what R is. R, we're told this is theta and this is L, and this is the distance R. So R is L sine theta, right? So it's the opposite side. And since it's the midpoint, they're both equally distant. So, right, so that would be what I would call a good answer. You can write, instead of K, the 1 over 4 pi epsilon naught. That would also work, right? This is probably the simpler one. But anything kind of like that. Now, we're into some Newton's laws stuff. What forces does charge 1 feel, basically, right? So we have charge 1. And There's some simple ones, right? Stuff you remember hopefully from physics 1. There's a string, so there's a tension. It has mass, so there's a weight, or mg, or the force of gravity. And there's also an electric force that we know is going to be repulsion, because they're the same sign of charge, right? So it's going to point kind of like that, right? And that's it, right? Just labeling the forces. And this is the last part, and this is kind of oddly worded, right? It takes a bit of practice to get used to. It's saying that using the conditions of equilibrium, and hopefully equilibrium makes you remember that that's something that's not accelerating, and that tells you should be thinking about Newton's laws. We have to write but not solve some equations. So that means I really don't have to do algebra, I just have to sort of organize the information. So my horizontal forces, we have the electric force in the negative direction, and tension, right, if I draw this kind of in there, this is theta, so it's T sine theta, and equilibrium tells us that that's 0. This is, right, the net force is 0 when it's in equilibrium. Right? In the y direction, I have a similar equilibrium statement. Right? This time it's T cosine theta upward minus the weight mg equals 0. Okay? And this is almost it. Right? All we need to do now is we need to write what's the electric force that charge 1 feels. So this, right, is Coulomb's law, negative k, and then we have to do the product of the two charges. They're both q, so that's q squared, and then we divide by the distance squared. Well, if the midpoint was a distance L sine theta, then this is just 2L sine theta, that distance squared. Right? And so this is one equation, and this is the other. And that's it. I don't need to do the algebra to solve. I have two equations, and I have two unknowns, right? Everything else is a constant or a given quantity. And so I could solve it if I wanted, but I'm not asked to do that. Just set it up, right? And so that sort of satisfies that condition, right? We used equilibrium, Newton's first law, to get two relationships that could be solved for the tension and the angle that these charges would hang at.